So welcome back to the ninth video of this course. We will begin further our journey with Alice and Bob in terms of the quantum world. So we can suppose that Alice sent some quantum information to Bob, and through this channel, this is a symmetric channel, but for a quantum symmetric channel, which is noisy. So now we have some quantum noise that we are interested in, because this is what drives the error procedures. So suppose that this channel is controlled by this kind of output density matrix, this quantum operation that is quantum noise. So here, quantum noise. That the information will be processed during this channel. So we can write down our operation element in the quantum error procedure. This is a operator sum representation for this density matrix, that we will have some kind of error when you start to make kind of what we say the bit flip, and 1 minus p, which is corresponding to the density matrix. There is no error happened, but we must say here that this is a bit flip operation, because bit flip what will create our error. This is bit flip. So we have those operators. This is environment operator with itself again. The conjugate is actually equivalent to E. We can write E as E, just E, operator E, with probability B. So let's write down a quantum code. We have been exposed to classical coding last video, but now let's make a quantum code. The quantum code is simply just n and k as we did, but the Hamming distance here is neglected for some reasons. But let's just neglect it for a while and say that this is an example for a quantum code. So 3 zeros can be written as a cat operator by logical zeros, and here logical 1 for this kind of codes. We can make a wave function. We come back to our wave function, but here it's a quantum code, as phi is equivalent to superposition of 3 zeros and 3 ones with their corresponding amplitudes A and B. Let's make what we did before. We will work out an error detection procedure and its probability with a wave function phi, and we will suppose that we are receiving a kind of 3 zeros and 3 ones, and here the probability of getting this is 1 minus p cube. No error so far. But let's suppose there's some bit flip operation that happened here. So we can make two. Let's first begin with one bit flip. So it can be 1, 0, 0 plus b with bit flip here 0, 1, 1. Or you make another one here with 0, maybe here another one 0, 0, 1 with 1, 1, 0, and the corresponding probability for this kind of operation is 1 minus p squared with p, right? Here 1 minus p squared with p, and here's the same. But if I do 2 bit flips together, I can say this 0, 0, 1, maybe have 0, 1, 0, 1 plus b 2. So it's isolated, we just change it this one, so I have to change that. B, so A is kind of 2 plus B. I know it's a bit boring, but we have to make it. So we do the flip here, so it's 0, 0, 1, so it's 1, 0, 0. And maybe we can add another last one, which is all. So it's just the same, you have another one, but Here you have complete flipping, okay? Complete flipping for both. The complete flipping will correspond to probability p cubed, because p an error. Here is 1 minus p times p squared is 1 minus the p times p squared, and also the same, right? So we call these kind of four mutually orthogonal bases, we call them, so let's just stick with this for a while, and let's call mutually orthogonal bases. And these are distinguishable from, these are distinguishable from these kind of errors that happened. These are mutually orthogonal distinguished bases with distinguished probabilities, and here is the error. So all of these states are important in quantum error correction that we will see in the next video, how we can correct those errors using even those orthogonal bases that we will have. So the next time we will make more just delving into the world of error correction using the syndrome operators. So we will be knowing this famous syndrome operators and their correction. But let me just first, or just lastly say that the quantum code of this kind of coding is important when I would like to identify the kinds of k-qubits, or say k-qubit subspace, which is part of the Hilbert space. So now I'm getting more wideness of the Hilbert space, and how can I error correct that in the corresponding space. So thanks a lot for watching, and see you in the next video.